Okay, let's begin with some new problems. Okay, again, I'll solve another fancy problem about Lagrange multipliers to show that this method works in any dimension. Okay, so this one is, I think I took this from the book. Okay, so second problem. Find the minimum, mean, and max of the function. So we have n variables now, x n, defined as their sum. Okay, so if it's a complicated function, we will be lost. Okay. Now, if we stop here, the minimum of this function is minus infinity. The maximum of this function is plus infinity. It's not interesting. But we restrict this function to a closed and bounded surface. And the simplest, most obvious one is the sphere. Okay, so we restrict this to the unit sphere in n space and try to find the minimum and maximum on the unit sphere, okay, given by g of x1 xn, which is x1 squared plus xn squared minus 1 equals 0. Okay. So, for example, if n is equal to 2, we are in the plane, we have a unit circle. So we want to find the minimum and maximum values of the sum of the coordinates on the sphere. If we are on the x-axis, for example, the point 1, 0 is on the surface, the sum is 1. But as you move, you see that if you go to the, just cut the circle with the line y equals x, we expect that the maximum of the sum will be there. Okay. Okay, so that's our expectation. So what happens on the sphere? Okay, so again, we can convince ourselves that there is a point farthest away from the origin in terms of this metric. Okay, we call such things roughly metric. Okay, so going back to the problem, you see that this is a closed and bounded object. Here we recognize that it is a sphere, so we know that it is closed and bounded. But normally, if you have a nice expression like this equal to 0, it is closed. And since these are real numbers, you see I cannot make x1 arbitrarily large. Okay, then minus 1 will never make it 0, and there are no negative things here to cancel that. So that tells us that this is bounded. The word close here is meant that when you are, there's no such thing as you are approaching to a boundary, but you are never reaching the boundary. Okay? So just like, for example, the open interval 0, 1. Okay, so that's an open thing. And what is the maximum of x when x is restricted to the open interval 0, 1? Okay, so the number 1 is comes to our mind, but x never takes the value 1. Okay, so there you have to use, to express this, you have to use another word. You say 1 is supremum of this, but it's not maximum of this. So to avoid these technicalities, we prefer to work on closed things. If it is not closed, then you have to be okay. Most of the techniques don't work. You just work on your own. Okay, so we totally understand this problem here. Minimum, this is a closed and bounded set. Okay. G equals 0 gives a closed and bounded set, okay, unit sphere, okay. Well, the dimension of this is n minus 1, so sometimes we say unit n minus 1 sphere, and sometimes the notation is s n minus 1. Okay, so these are the notations. So global mean and max exists for f on our surface. Okay, so you do this once, now you know what you are calculating. Okay, you see this is crucial because in the previous example, we found only 1 point. Okay, so now if you didn't think about it until this point, so is this going to give you minimum or maximum? Okay, so there is no indication in the technique, in the method, to show that this is going to be either one. So you have to decide this. So we decided here. This has this has both mean and max. Now we apply Lagrange multipliers. Lagrange multipliers method. Okay, so sometimes we say apply Lagrange multipliers, and sometimes we say apply Lagrange, and Lagrange turns over in this gray. Okay, so we calculate the gradient of f. You see it's a very nice gradient, 1, 1, 1. We calculate the gradient of g. Okay, I'm not writing x's here. So this is equal to, again, everything is 2, so I take 2 out. This is x1, xn. Okay, so Lagrange multiplier says that I have to set gradient of f equal to lambda times gradient of g. Okay, now I write what this means. So 1 is equal to lambda times x1. Okay, so everything is 1, lambda times xn. Okay, so here I am tempted to say that x1 is equal to 1 over lambda. So in this case, it is clear I can do it, but in more complicated problems, the complicated only means that this system is complicated, okay? You see, otherwise the idea is very simple. You don't immediately divide by lambda. You say there are 2 cases. The first case, lambda is 0. The second case, lambda is different than 0. When lambda is different than 0, you divide by lambda, you do your simplifications, and you get a result. But surprisingly, in some cases, when you go back and say, now suppose lambda is 0, so I can't divide, you get another solution, okay? So if you don't do this, you miss some of the solutions. In this case, it is clear because this side is 1. Lambda cannot be 0, okay? So here we say, here, clearly, in mathematics, you try to avoid the word clearly because when you say clearly, it means I'm not sure about this, don't ask me any questions, okay? If you ask, I'll treat you like you are stupid, okay? But here it is clear, okay? So clearly, lambda is different than 0. So we know it is because 0 times will not give 1. So we can divide by lambda. So x1 is equal to 1 over lambda. All of them are equal to 1 over lambda. Okay, so this is the most information I'll get from this. Fortunately, I have another equation, so I go back to that. So that equation will tell me, I'll put these into that equation. That equation will tell me what lambda is. Nobody cares about lambda except that if I know lambda, I know x1, xn. Okay, so that's what I'll do. Equals 0. Okay, so g is equal to 0 is 1 over lambda square plus 1 over lambda square is equal to 1. So I have n of these things. I have n over lambda square equals 1. So lambda square is equal to n. Lambda is equal to plus or minus square root n. Okay? So each of them have the same sign with respect to lambda. So the solution, so we get 2 points here. Okay, so we get square root n, and minus square root n, minus square root n. Okay, so let me check if I got the same things here. No, xn's are 1 over the square root. Okay, so let me remind me here myself that xi is 1 over, so plus or minus 1 over square root n. I is from 1 to n. Okay, so we get 2 points here. So the first one, okay, let me put the plus or minus in the front. 1 over square root n, 1 over square root n. Okay, so we know that a global maximum exists. We know that a global minimum exists. We have 2 points. So we are sure at this point that one of them will give us absolute minimum. The other one will give us absolute maximum. The function is nice. We just add them up. Okay, so f at positive square roots will give me n of these, n over square root of n. So this is maximum, max value, because it is positive. The other one will give me negative, minus 1 over square root n, minus 1 over square root n is minus n over square root n, minus square root n, mean value. Okay, so what does it say, for example, in the plane x, y, I have this circle. So this point and this point. Okay, so this is 1 over square root 2, 1 over square root 2, and this is minus 1 over square root 2, 1 over minus square root 2. Okay, so f, so let's call this P1, let's call this P2. F of P1 is square root 2. You see that it is larger than 1 because the first thing that comes to mind is this point. This is 1, 0. F at this point, f 1, 0 is 1, but this is square root 2 larger than 1. Okay, so at least it makes sense. Of course, this calculation does not prove that it is the maximum. It just makes us feel comfortable with the result. It's really large. Okay, so on the sphere again, at one point, because if you move this to other octants in the sphere, for example, one of them will be plus, one of them will be minus. So here, for example, at this point, f will be 0. Okay, so here, so this is minus 1 over square root 2, 1 over square root 2. So f of this is equal to 0 here. Okay, so we totally understand this problem. Okay. So now let me solve a problem with a little bit more calculation. So I think I did this. Okay, so this will show us that even if you make this a little bit non-trivial, the calculations become long because you are going to solve two nonlinear equations in general. I think this is number 3, right? Find the closest and farthest points from the origin on the ellipse x squared plus xy plus y squared minus, so equals 1. Yes, that's the thing. So before we apply anything, let's look at how we find this. To find the distance, we consider circles starting from the origin. All the circles will have center at the origin. You start with circle with radius 0, and then you start to increase the radius. When the circle touches the ellipse, that's the first time the circle touches the ellipse, the radius of the circle is the smallest distance. This is a symmetric ellipse, as you see. Okay, so you take a normal ellipse, just tilt it a little bit. So it will touch the ellipse at 2 points simultaneously. That's the smallest distance. Then you continue to increase the ellipse, the circle, until it touches the ellipse for the last time. If you make it a little bit larger, now the ellipse will totally lie in the circle. So the last time it touches the ellipse, you check the radius, that's the maximum value. Okay? So we totally understand the geometry of this. So let's see if I can draw this. Okay, so this is, suppose this is an ellipse, and then we have this promised circle here. This touches this, and then we have this other, well, it didn't look. You draw a circle either at your first attempt or you never draw it, so I'll prove that now. Okay. So Okay, so this is our ellipse. This is x squared plus y, xy, x squared plus xy plus y squared equals 1. Okay, let's put also some coordinates there. This is x, this is y. Okay, so this circle has radius r1, and this big circle has radius, okay, let's say small r, big R. Okay, so this circle has equation x squared plus y squared equals r squared. R is the minimum distance referring to this problem. Okay, and this big one is x squared plus y squared equals r squared. R is the max distance. Okay, so this is the nature of the problem. Since this is symmetric, you can solve this without using derivatives, because you see this ellipse just turned around like this. So if you look at y equals x line, find where it intersects here. No, y equals x line is this. This is y equals minus x line. Okay, and then you find this intersection and take this distance and take this distance. That will also give you the answer without any derivative. So we are using this problem to demonstrate how Lagrange multipliers work and how painful it is sometimes to go through these equations. Okay, so let me go over it. Apply Lagrange. Okay, so we have to calculate the gradient. Okay, so here f of x, y, we are now in 2 dimensions, is x squared plus y squared. Okay, square of the distance function. Okay, so at this point I make a note in my mind. At the end, shall I get the square root of the answer I find or not? If distance is asked, at the end I have to take the square root. I check the question, says find the points. Okay, so I will not take any square root. I will not mention about the distance. So what the question asks are these points only. Okay, so the question is about points. So I'm asked to find these red points. Okay, so I can now forget about taking square roots. The constraint is gxy equals x squared plus xy plus y squared minus 1. This is equal to 0. Okay, so the rest is now routine. I look at gradient of f. This is 2 times x, y. Okay, so again, I'm taking 2 out so that I will not carry it all through the calculations. I look at gradient of g. This is 2x plus y and x plus 2y. Okay, so I write, next I want to write this, gradient g. So that tells me that x is equal to lambda times 2x plus y, and y is equal to lambda times x plus 2y. Okay, so I want to solve this together with x squared plus xy plus y squared equals 1. Okay, solve this system. Okay, so Lagrange multipliers brings you up to this point. Okay, so this is where the method took you. Now the method leaves. You have to work with these on your own. Okay, so here, this is what I taught last night. If I write it now, I'll write it in a different way. If I ask everybody to solve this, everybody will probably solve it in 2 different ways, unless you pick your friend and then copy his method. So I'm saying this to make you comfortable, because sometimes you look at this and you say, what is the correct way to approach? There is no correct or wrong way to approach to this. Okay? Whatever you do will work. You play with this equation. While you are playing with it, you start getting some new ideas, and then you cross whatever you do that far, and with the new idea you solve it. Okay? So this is how I managed to solve this. So from the first equation, so let's give numbers. Generally, this is very helpful in working with the Lagrange multipliers. You give numbers to this, and then you write which equation you use to do what. Okay, not because you want to explain it to others. Well, that's also in your mind, but later when you are checking, you will be surprised that what you did 5 minutes ago is a mystery to you. So you have to explain to yourself what you are doing. It also helps in the exam, because when we are reading your exam, we can only read what is written on the paper. We cannot read your mind. So even if you mean that x equals 0, if you write here x equals 5, we read it as x equals 5. Okay, so these things happen. So that's why I'm mentioning it. Okay, so what do I do here? So let me emphasize that my solution, okay, so everybody will have, yours will be different, So I keep emphasizing this because I know the feeling that how do they solve this? That's the wrong question. The correct question is, there's no question, you just start playing with this. Okay, so what I thought when I looked at this is, you see in the first equation, y is easy. This has a coefficient in it, so y is easy. Maybe I solve for y, put it into the others, and keep going. But solving for y means that I'll divide by lambda. So what if lambda is equal to 0? So let's first get rid of that case. If lambda equals 0, see x equals 0, y equals 0. I put it here, I don't get 1. Okay, so lambda is not 0. So first, if lambda equals 0, then from 1 and 2, we get x, y equals 0, 0. But then 3 is not satisfied. Okay, so lambda is different than 0. Okay, so that's a relief. So whenever I want, I can divide by lambda. So let's see. From 1, I get y equals 1 minus 2 lambda over lambda times x. Put this into the second equation. Okay, so I get 1 minus 2 lambda over lambda times x equals lambda x plus 2 lambda y. Plus 2 lambda y. But y is this, so let me put y into parentheses to emphasize what I'm doing. 1 minus 2 lambda over lambda x. Okay, so now the thing to do is write this. You see, there is x here, there is x here, there is x here. So you bring it to, you take x out. It will be a polynomial in lambda times x equal to 0. So that polynomial turns out to be 3 lambda squared minus 4 lambda plus 1 x equals 0. Okay, so now again we have two cases. Either x equals 0 or x is different than 0. Okay, so I have to get rid of that case first. When x equals 0, you see here I have 0, here I have 0. That forces y to be 0. I again have this, which is not a solution. Okay, so if x equals 0, so from 1 we get y equals 0, but 0, 0 does not satisfy 3, so x is different than 0. Okay, so that now, okay, so let me take this down, or maybe, okay, here I'll do it. So now that polynomial is equal to 0. That will give me two solutions, which is good because I'm looking for 2 points. Okay. Okay, so this polynomial is 0, 3 lambda square minus 4 lambda plus 1 equals 0. So this has two roots. Okay, so let's say lambda, both roots are equal, so I use the long form. You can use half formula here, but then you'll divide with 3 anyway, so it doesn't help. So I use 4 kere 4 16 eksi 12 divided by 6. Okay, so you simplify this, you get two solutions. One of them is 1, and one of them is 1 over 3. Okay, because here you have square root of 4, that's 2, so everything works nicely. Okay, so taking one case, so case when lambda equals 1. Okay, so let's see. Now we go back to this. Okay, so let's give a name to this, 4. Okay, from 4, we get y equals minus x. Okay? And when lambda equals 1 over 3, from 4 we get y equals, I think, x. Okay? So now we'll put these into next. We put these into 3, the constraint. Okay, so where is the constraint? Here. Okay, suppose x and y. First, let us look at the first case. X and y have opposite signs. So x squared minus x squared, this goes, and you have x squared equals 1. So x equals plus or minus 1. Okay. So the first case, y equals minus x. So this gives you x squared minus x squared plus x squared equals 1. So this gives you x equals plus or minus 1. Then y equals, you see, of opposite sign. So this is minus plus 1. So the solutions we get here are 1 minus 1 and minus 1 plus 1. Okay? So as a habit, we put these in boxes. These are good points. And when y is equal to x, the second case, we have x squared plus x squared plus x squared equals 1. So x equals plus or minus 1 over square root 3. And y is the same, so this is also equal to y. So the points we have are 1 over square root 3, 1 over square root 3, and minus 1 over square root 3, minus 1 over square root 3. So these are the other points. Okay, now we calculate f at these points. So let me see where I calculate them. Now we calculate f at these points. Okay, so f of, you see f is taking square, so f doesn't bother about the signs, so we can put plus or minus here. So plus or minus 1 minus plus 1, it will give me 2, right? So the other one, f plus or minus 1 over square root 3 plus or minus 1 over square root 3. So this gives 2 over 3, right? 2 over 3. Okay. So these points, conclusion, so it always helps to write the conclusion. The closest points are, as we expect, they are symmetric. Okay, so you see one of them is minus 1, the others. From the picture, Okay, I'll come to the picture in a minute. So these are the closest points. And farthest points are these things, okay? So plus or minus 1, minus plus 1. Okay? So remember in the picture we had this small one and then this large one. Okay, so and the ellipse was something like this. Okay, so these are these points, and these are given by these points. Okay, as we expected. Okay, so this is one Lagrange problem. So let me see if I have an interesting one. Okay, so we have another one, but let's okay, I'll just go over this. I will not solve this in detail because you see the main thing is to solve this. You see, we wrote the problem. We totally understood whether there was a min or max. We immediately came to this step, and from there on we do two boards of calculation. Okay. Mm-hmm. Lambda is an auxiliary value, and its value is not asked in the question. It doesn't play any role in the answer. So if you say, no, the only purpose, we don't want lambda because of the following reason. The only reason we want lambda is that it algebraically translates the sentence that the gradient of f and the gradient of g are parallel to each other. Okay, so that's the only information we want, and lambda gives us that information. If somehow we wanted to understand that the length of gradient of f is some constant times the gradient of g, and what is that constant, then we need lambda. But that never makes any sense in this problem, because the reason why we came to using lambda is we had a dot product equals 0. So what is the meaning of this dot product? We translated to algebra, and there popped up the auxiliary parameter lambda. So that's why we don't calculate the value of lambda. Okay. But in some problems, like the previous one, you have to calculate lambda because that's how we attack the system. You calculated the value of lambda, then value of x and y depended on lambda. But after you find again the value of x, nobody cares about what lambda was. Okay? Okay, any other questions? Okay, so this next one, I'll just write the problem, set up the system, and then maybe I'll just write the answer because you see it takes so much time. So watching someone solve a problem on board is like watching ice skating. You see how smooth they skate on ice. But if you are not accustomed to this, just put those skates on, go onto ice, and you'll see how smooth it is there on the ice. So you have to solve a lot of problems. Start with the simple ones until you feel that no matter which problem comes, okay, it will take time, but you know how to attack it. Okay, then you can stop. So this problem is again takes a long to solve, but this is just an algebraic question now. But again, you can draw pictures. Find the min and max of f of x, y, z equals x cubed plus y, z on g, x, y, z, which is given by x squared plus y squared plus z squared minus 1 equals 0. So again, if you want to draw a picture, that x cubed y squared equals a constant k is a surface, okay? And as you change k, it moves away from the origin, okay? This is a sphere, unit sphere, and you want to find the minimum value of k and the maximum value of k when you hit this sphere. Okay, so since in 3 dimensions it's not easy to draw this, we don't draw pictures, we just look at this. We recognize this as a sphere, so this is a closed and bounded set. Okay, so sphere, closed and bounded. Okay, so we'll look at this, a polynomial. So continuous for us. Okay, so we put these two things together. F has a global mean and max on this sphere. Okay, so we get rid of this technical detail from the beginning. Now we know that the solution will make sense. Okay, we will find several values. The smallest of those values will be the minimum. The largest will be the maximum. Okay, then apply Lagrange method, Lagrange multipliers method. Okay, so gradient of f is equal to 3x squared and z and y. Gradient of g is again 2 times, to make life easier, x, y, z. So the system is, and what I want to write from here is gradient of f is equal to lambda times gradient of g. So I start writing this. 3x squared is equal to lambda x. Z is equal to lambda y. Y equals lambda z. So at this point, you realize that this is a cooked up exercise for a class because these two equations will make life very easy. Okay. And then we have, of course, the constraint. We have x squared plus y squared plus z squared equals 1. Okay. So this is equation 1, equation 2, equation 3, equation 4. So we want to solve this system. Okay, so again, now you start playing with this. So again, the first thing, by looking at the shape of this system, the first thing that comes to my mind is again to check what happens when lambda is 0. So I immediately get rid of this, and then I say lambda is now different than 0. So whenever I need, I'll divide by lambda. If lambda is equal to 0, you see that x, y, z is 0 from the first equations. You put that into the fourth equation, it's not satisfied. So lambda is different than 0. Okay? So that is how I would begin, but you can start in a different way. The reason, again, I keep repeating some obvious things is because it is very, very possible to, very humane to forget these things. Sometimes you forget the case when lambda is equal to 0, and it turns out that there's a solution. In the examples we did, lambda equals 0 did not give any solution. So if you forget to examine the case lambda equals 0, you will not miss anything in these examples. But in most examples, lambda equals 0 gives you some solutions. Lambda different than 0 gives other solutions. And you have to check all the solutions. Okay, so I'll just write the solutions. Okay, so because we are running out of time, one solution is this. So this is actually 2 points: 0 plus or minus 1 over square root 2 plus or minus 1 over square root 2. So we have 2 points here. I have another 2 points: 0 plus or minus 1 over square root 2, but minus plus 1 over square root 2. And, well, I came here when I take lambda different than 0. If lambda is different than, well, lambda is different than 0. If x is equal to 0, I get these things. Okay, x equals 0. If x is different than 0, then I get, first, this is the easy case. I get plus or minus 1, 0, 0. Then I get 2 more points, well, 2 sets of points, 1 over 3 plus or minus 2 over 3 plus or minus 2 over 3, and P5 minus 1 over 3 plus or minus 2 over 3 minus plus 2 over 3. Okay? So you see that plus or minuses change sign when you solve these things. Here you will have a lambda square inevitably. Okay, so that explains why you have these plus or minuses here. Okay, now you calculate f at these points. F of P1 is 1 over 2. F is, so they are of the same sign, so it doesn't matter whether you take the plus ones and negative ones, because here this is yz, okay, y times z, it will kill the signs. So f of P2 is minus 1 over 2. F of P3 is plus or minus 1, depending on whether you are taking plus or minus here. F of P4 is 13 over 27, so this is less than half. F of P5 is equal to minus 13 over 27. Okay, so these are half. This is approximately half. So the largest one is here. Plus 1 is the largest one, minus 1 is the largest one. Okay, so from here, so maximum of f is at 1, 0, 0, and max value is 1, and minimum of f is at minus 1, 0, 0, and minimum value is minus 1. Okay? So these are the routine parts of the Lagrange multipliers, and of course the time will be spent on finding these solutions. Okay? So again, if you approach this systematically, the solutions will come out quite easy. Well, not quite easily, but at least you will not feel whether you lost some solution or not. Always go systematically, okay, by looking at this. Case 1, lambda equals 0. What happens? Okay, case 2, now lambda is different than 0. Under that, another case, x equals 0. X is different than 0. Okay, so in this problem, that suffices to solve the problem. Then you get all the solutions. Okay. So we have. So I think we can stop here today. I was planning to solve review problems for the exam, but in 5 minutes, I can only confuse your mind. So today we did Lagrange multipliers. This will show up in the next exam. But for this exam, everything we did up to including on Monday. I have an office hour today. You can also send me email. Okay, so I can answer the emails. Okay, good luck in the exam.